Hey everyone, and welcome to today's Explainer. Think of this as your absolute masterclass for Section 4.4 of our software engineering textbook, all about requirements specification. It is so fantastic to have you here. Today, we're going to learn exactly how to transform messy, unpredictable human conversations into a crystal clear, structured blueprint. A blueprint we can actually use to build a working software program. We're going to take this nice and slow, step by step, to make sure you understand exactly how to define system behavior perfectly. So here's our game plan for the day. We'll start with what requirements specification actually is, then look at natural language specifications, structured specifications, visualizing with use cases, and finally the SRS document and your exam prep. We really need to lay this solid foundation before we even think about writing complex code. Okay, let's dive right into this first section. What is requirement specification? In our previous chapters, we talked all about elicitation, right? The process of talking to stakeholders and gathering their needs. Well, once we've gathered those, we absolutely must write them down clearly. So let's define our first major term for those of you learning this for the very first time. Requirement specification is simply the process of writing down the user and system requirements in a document. The whole goal here is that these written requirements must be clear, they must be completely unambiguous, and they ultimately act as a contractual blueprint between the customer and the software developers. Now listen up, because this is a super common mistake students make, mixing up the two main types of requirements. Let's make sure we distinguish between them clearly right now. User requirements are broad, abstract statements written in natural language. They're meant for the client or managers to read, so they should literally only describe the external behavior of the system, absolutely no technical jargon. On the flip side, system requirements are expanded, highly detailed versions of those user requirements. These are written specifically for you, the software engineers. They include specific functions, exceptions, and even initial architectural constraints. Let's look at a practical example of this from the textbook regarding the MentCare system, which is a system that manages mental health care information. Notice the user requirement at the top. It simply states the system shall generate monthly management reports showing the cost of drugs. It's super easy for a clinic manager to understand, right? But below it, the system requirement expands that single sentence into highly specific constraints. It tells the software engineer exactly when the report runs, after 17:30 on the last working day, and exactly what data fields must be present, like the number of doses and the total cost. Basically, the broad user goal transforms into a strict engineering blueprint. All right, moving right along to Section 2, Natural Language Specifications. Plain English is by far the most common notation used out there in the industry because it's expressive and universal. But as we all know, human language is highly prone to ambiguity and vagueness. To fight that ambiguity, we have a strict standard we must follow. I like to call this the golden rule of natural language specification. And honestly, you should definitely highlight this for your exams. You must use the word shall for mandatory requirements. These are features the system absolutely must support to be accepted by the client. Conversely, you use the word should for desirable requirements. These are features that are, nice to have, but not strictly essential for the final delivery. And this brilliantly illustrates that golden rule in action. Take a look at this example from the automated insulin pump embedded software. It says, the system shall measure the blood sugar and deliver insulin every 10 minutes. It uses shall because if this embedded medical device fails to measure blood sugar, a patient's life is literally at risk. It is strictly mandatory. Similarly, the self-test routine shall run every minute. There is zero room for misinterpretation here. Beyond the golden rule, the textbook gives us some incredibly helpful guidelines for writing good natural language requirements. You must standardize your format to make omissions less likely. Keep using shall and should consistently. Use bold or italic text to really highlight key parts. Avoid technical jargon so the client can actually read the thing. And finally, always include a rationale. You must write down why the requirement exists and who asked for it. That way, if a conflict arises later, you know exactly who to consult to clear it up. So, to summarize, plain English is great, but we have to enforce strict rules to keep it usable. Even with all those great guidelines, natural language can still leave things open to interpretation when we start defining really complex software behavior. So I have a question for you. How do we further reduce the ambiguity of free-form text when we hit that really complex logic? Well, the answer brings us to Section 3, Structured Specifications. The solution to free-form ambiguity is using standard forms or templates. When we use a structured form, we treat it almost like a rigorous checklist. Every single time you define a function, you must document these specific fields. 1. What are the inputs and where do they come from? 2. What are the outputs and where do they go? 3. The preconditions, meaning what must be true before this function is called. 4. The postconditions, what is true after it finishes. And 5. Are there any side effects? You're going to be using this exact checklist in your own university projects to ensure your specifications are completely bulletproof. Now, alongside those forms, structured specifications often utilize tables. Tables are absolutely excellent for defining complex alternative computations. Look at this exact textbook logic for the insulin pump. Instead of writing a messy, confusing paragraph filled with a bunch of nested if-then statements, we just use a clear table. If the sugar level is falling, meaning reading 2 is less than reading 1, the computed dose is 0. We can easily step through every single alternative condition, perfectly calculating the dose without any linguistic ambiguity whatsoever. All right, let's transition into our fourth section, visualizing with use cases. We're shifting our focus away from text and tables entirely and moving toward graphical notations. This introduces us to use cases. We need to define this term clearly. Use cases are a graphical notation which is part of the Unified Modeling Language, or UML. Visually, stick figures represent the actors, which can be human users or even other computer systems, and ellipses, or ovals, represent the interactions they have with the system. Mapping out these actors and interactions gives you a fantastic, high-level visual blueprint to validate with your client before you go off and write thousands of lines of complex Java code. Now, what's really interesting about this slide is that use cases aren't just little drawings on a whiteboard. Once you have the visual model, you expand it into a structured tabular description, like the kids take pics upload use case we see here. It details the actors involved, the normal sequence of events step by step, and, crucially, what happens when things go wrong, the exceptions. For example, if a user uploads a photo with a duplicate name, this specification tells the system exactly how to handle that error. So we have natural language, structured forms, tables, and use cases. This brings us to Section 5, the SRS document. Because we have to ask, where do all of these different models and definitions ultimately live? Well, they live in the Software Requirements Specification, commonly known as the SRS document. Let's define this clearly. The SRS is the official statement and contractual blueprint of exactly what the system developers must implement. It integrates both the high-level user requirements and those highly detailed system requirements into one absolute source of truth. Because it is that central source of truth, it has a very diverse readership. The textbook specifically outlines 4 distinct audiences, and honestly, you must know these for your exams. First, customers read the SRS to check if it actually meets their needs. Second, managers read it to plan project schedules and budgets. Third, system engineers, that's you, read it to understand exactly what you need to build. And fourth, system test engineers read it to develop the validation tests that will actually prove the software works as intended. Now, to give you a fully rounded view of modern software engineering, the textbook does present a counter-argument to all this heavy documentation. Agile development teams often argue that massive SRS documents go out of date almost instantly as business needs change. So instead of a thick contractual document, they prefer writing brief user stories on index cards or whiteboards, continuously adapting as they code. The textbook notes this is highly relevant for business systems with unstable requirements, though, of course, critical systems, like that insulin pump, still very much rely on a rigorous SRS. So the crucial point is that understanding how to formally specify requirements is the absolute bedrock of reliable software engineering. Let's wrap up today's lecture by summarizing our key takeaways and focusing on your exam preparation. If you're cramming your notes tonight, here are the absolute most important concepts to memorize for your tests. First, you must be able to define the strict differences between user requirements, which are broad and non-technical, and system requirements, which are detailed engineering blueprints. Second, memorize that golden rule of natural language. Shall is mandatory, should is desirable. Finally, be able to list and explain the 4 diverse audiences who read the SRS document: customers, managers, engineers, and testers. If you take away literally one thing from this entire chapter, it's this. The specification phase is where the magic of translation happens. We take messy, ambiguous, sometimes contradictory human conversations, and we transform them into a structured, contractual blueprint that software engineers can actually build from reliably. And that wraps up our look at requirements specification. But before I let you go, I want to leave you with a somewhat provocative thought as we prepare for our next topic on system modeling. You've spent all this time writing the perfect, strict specification blueprint. But how will that document hold up when your customer calls tomorrow and completely changes their mind about what they want? Think about that, and I'll see you in the next explainer.